Every perturbation model must make 5 decisions. 5 architectural choices that determine what the model can learn and what it will miss. First, how do you encode the cell? The cell's gene expression profile contains thousands of measurements. You need a representation that captures its identity. Second, how do you encode the drug? A molecule is a 3-dimensional structure. You need to compress it into something a neural network can process. Third, how do you combine cell and drug? This fusion step determines whether the model sees cell and drug as independent inputs or as interacting partners. Fourth, how do you decode the prediction? And fifth, how do you measure whether that prediction is any good? These last 2 choices shape the output. Same blueprint. Different tools at each step. 3 teams looked at this blueprint and reached for different tools. The choices they made define their model's strengths and its blind spots. PrePR-CT starts with the cell encoder. Their choice here shapes everything that follows. They build a co-expression graph. Each gene becomes a node. Genes that tend to go up or down together get connected by an edge. The graph encodes what biologists already know about gene relationships. But a flat graph treats every connection equally. That's not realistic. Some gene pairs are deeply coupled. Others are loosely correlated. So they add attention. Graph attention lets the model learn weights for each edge. Some connections get amplified. Others get suppressed. The model can now tell you exactly which gene relationships drove its prediction. That's interpretability built into the architecture. Now the loss function. This is where most models get it wrong. Single-cell data is not a single number per gene. It's a distribution. If you measured the same gene in 1,000 cells, you get 1,000 slightly different values. Using mean-squared error would collapse all that biological variability into a single point. You'd lose the shape. Earth-mover's distance solves this. It treats the predicted and observed profiles as 2 piles of Earth and measures the minimum cost of reshaping one pile into the other. It preserves the full distributional shape. But here's the trade-off. Imagine a walled garden. Inside the walls, everything flourishes. Flowers bloom, pathways connect, the gardener knows every plant by name. That's what the graph gives you, rich, structured knowledge about genes that are connected. But outside the walls? Wilderness. Genes that aren't in the graph are invisible to the model. They might be important, but the model will never see them. You must build a separate garden for every cell type. PrePR-CT's graph attention gives you interpretability and structure, but only within the walls you've already built. PRnet takes a completely different approach. They start with the drug encoder. Every molecule can be written as a smile string. It looks like a chemical formula mixed with punctuation. It's a text representation of 3-dimensional molecular structure. RDKit converts that text into a fingerprint. A fixed-length binary vector where each bit encodes whether a particular molecular substructure is present or absent. No pre-training. No learn parameters. Pure chemistry. And this is the trick that enables massive scale. 1 compound. 100. 1,000. 175,000. Including molecules the model has never seen during training. The fingerprint doesn't care. It works on any valid smile string. Now the decoder. This is where PRnet diverges from conventional thinking. Instead of predicting a single expression value per gene, PRnet uses a conditioned variational autoencoder. It encodes into a latent space. Not a point, but a cloud of possibilities. Each position in that cloud represents a slightly different cellular state. When you sample from the cloud, you get a different plausible expression profile each time. The VAE generates distributions, not point predictions. This captures the biological reality that cells respond with variability, not precision. But the trade-off. Imagine a shapeshifter trying to fit through different doors. A square door? It squeezes into a square. A triangle? It reshapes again. A star? It stretches to fit. It gets through every door, but look closely, and you'll see gaps around the edges every time. That's the fingerprint. It represents any molecule, but it never captures the full three-dimensional detail of any single one. And the VAE adds another layer of compromise. It generates distributions, not sharp predictions. The shapeshifter fits everywhere, but grips nothing tightly. PRnet trades depth for breadth. TranSiGen makes the most radical choice of all. It starts with the loss function, and that choice changes everything. The data goes in. Raw gene expression measurements enter the encoder. The encoder compresses the data into a compact representation. Then a decoder attempts to reconstruct the original input. And the loop closes. The model compares its reconstruction to the original input and learns from the difference. No external labels. No curated annotations. The model teaches itself by trying to reproduce what it was given. This is self-supervised learning. Now the architecture. TranSiGen doesn't use a single autoencoder. It uses two separate VAE encoders. One processes control profiles, the untreated cells. The other processes perturbed profiles, the drug-treated cells. Each produces its own latent representation, its own compressed summary of the cellular state. And between them, a bridge. The bridge network takes the control latent code plus the drug features and predicts what the perturbed latent code should look like. It learns the perturbation mapping in latent space, not in the high-dimensional gene expression space. The bridge is the model. But the trade-off. Imagine an echo chamber. You shout into a cave, and the echo comes back, perfect, faithful, exact. The model learns to reproduce that echo flawlessly. But here's the problem, an echo only repeats what's already been said. It cannot predict a sound it has never heard. Reconstruction is not prediction. TranSiGen proves it understands the data it was given, but that doesn't prove it can predict a response to a new drug. And it's limited to 978 landmark genes. Self-supervision removes the label bottleneck, but the echo is not the voice. Every one of these choices had viable alternatives. The design space is far denser than these three teams explored. For the cell encoder, SCGPT and GeneFormer are foundation models pre-trained on millions of cells. Graph transformers capture long-range gene interactions that GAT might miss. For the drug encoder, ChemistryBERT and Molformer are molecular language models. Graph neural networks learn directly from the molecular graph. Cross-attention instead of concatenation. Diffusion models or flow matching instead of VAE. Silkhorn divergence instead of earth movers distance. The question is not which tool is best in the abstract. It's which tool matches your data, your compute budget, and your interpretability requirements. If you built a drug response model today, with access to everything available in 2026, every single box in this pipeline would change. The cell encoder becomes a foundation model. SCGPT or GeneFormer, pre-trained on 33 million cells. No more building graphs from scratch. The model already understands cell identity. The drug encoder becomes a molecular foundation model. Molformer or Unimol, pre-trained on over 1 billion molecules. No more engineering fingerprints by hand. The fusion layer becomes cross-attention. Cell tokens and drug tokens attend to each other directly. The model learns which parts of the cell interact with which parts of the drug. The decoder becomes flow matching. A generative model that produces sharper, more realistic samples than any VAE. And the loss becomes Silkhorn divergence plus contrastive alignment. Distributional matching that's orders of magnitude faster than Earth movers distance. The full pipeline is assembled. Every box has been upgraded. Imagine 5 puzzle pieces, each from a different box. A cell encoder trained on millions of cells. A drug encoder trained on billions of molecules. A fusion layer, a decoder, a loss function, each designed independently by different teams. But they were all built to the same standards. The edges align. The interfaces match. They snap together into a single coherent pipeline. No graph construction. No fingerprint engineering. Better sample quality. Faster training. The pieces exist today. The integration is the next paper. So how do you choose? Start with one question. Do you have access to foundation model embeddings? If yes, take the 2026 path. Cross-attention, flow matching, Silkhorn divergence. The full modern stack. If not, ask yourself, what is your primary constraint? What limits you most? Small data? Use PrePR-CT. The graph structure provides inductive bias that compensates for limited training examples. Novel compounds at scale? Use PRnet. The fingerprint representation generalizes to molecules never seen in training. Noisy data with no labels? Use TranSiGen. Self-supervision turns noise into signal. The complete decision framework. Each path is valid. Each encodes different assumptions. Architecture is not neutral. Every choice you make, from the cell encoder to the loss function, encodes an assumption about your data. The best model is the one whose assumptions match your reality.